వచ్చారు అమ్మగా వస్తేనా ফোনে চলে এসছে Okay, good afternoon all of you. Today's topic is simple harmonic motion. So there is a particle which is performing a circular motion, and in that circular motion the radius of the circle is capital A. Okay, capital A is the radius of the circle, and so the radius of the circle is capital A, and angular velocity of the particle is omega. Okay, uniform angular velocity is omega. So after a time t, the particle started the journey from P. After a time t, the particle will reach P dash, and this angle will be theta equal to omega into t. So omega is the angular velocity, and after a time t, the angular displacement theta will be omega into t, and the particle will move from p to p dash. So the x component of the particle's location at p dash, the x component, it will be equal to a cos theta. So the x component of the particle's displacement, it will be x equal to a cos theta, and in this formula instead of theta you have to write omega t. So the answer will be a cos omega t. So x equal to a cos theta. So finally that will come x equal to a cos omega t, right? So this is the x component of the position of the particle. Now when the particle started the journey, it was at p. Then after some time the particle will reach the point q. So when it reaches the point q, the x component of the position will become 0. Then after some time the particle will reach r. So when the particle reaches r, the x component of the velocity will become minus a, and when the particle reaches s, the x component of the velocity will again become 0, and finally it will come back to p. The x component, not velocity, the position, will again become capital A. So what is happening is that in one full circular motion, the x component of the position of the particle is changing from capital A to 0 to minus a to 0 and back to capital A. So whenever there is any to and fro motion, whenever there is any to and fro motion means that an object or a particle is going to a certain place and coming back to where it was. So that is called to and fro. So whenever there is any to and fro motion, that is called oscillation. And if the oscillation happens at a regular interval of time, then it is called a periodic oscillation. That means you know that so that means you know that the time period of rotation, time period is suppose t, it will be 2 pi divided by the angular velocity. So time period is, suppose the symbol of time period is capital T. So you are aware that omega is the angular velocity. So 2 pi divided by omega is the time period of angular motion, capital T equal to 2 pi by omega. So after every time interval of 2 pi by omega, it will come back to the same place. So it is oscillatory motion because to and fro, but it is also periodic motion because it is coming back to the same place again and again. So it is oscillatory plus it is periodic, right? So this kind of a motion is oscillatory and periodic both. Now x equal to a cos omega t. So velocity is dx by dt is minus a omega sine omega t, and acceleration is dv by dt that is minus a omega square cos omega t. So x is a cos omega t, v is minus a omega sine omega t, because v is derivative of x, so minus a omega sine omega t, and acceleration is dv by dt, so derivative of velocity, so minus a omega square cos omega t. So let's be very clear about one thing. We are not actually interested in the circular motion, we are interested in the x component of the circular motion. So the x component of the circular motion is given by this formula. Velocity of that means the x component is this, and acceleration of that is this. Now the acceleration which we have got, if you look at it carefully, then the acceleration is minus omega square into x, because there is a minus, then omega square, and whatever else is there, that is x. So the acceleration is minus omega square x. So what is happening is that the x component of the position of the particle is undergoing oscillatory, there is an oscillatory motion involved, because the x component is fluctuating from a to 0 to minus a, back to 0, and then back to a. It has got a periodicity, because at every interval of 2 pi by omega it is coming back to the location x equal to a. And now we have one additional information, that the acceleration is proportional to displacement. So a is acceleration, x is displacement. The acceleration is proportional to displacement, and there is a minus sign. That means the acceleration is proportional to displacement and it is oppositely directed to the displacement. So a is proportional to x and a is oppositely directed to x. So this kind of a oscillatory periodic motion is called simple harmonic motion. So simple harmonic motion is necessarily oscillatory, it is necessarily periodic, but beyond that it has got another quality, that the acceleration at any point of time is proportional to the displacement and it is directed oppositely to the displacement. So a is proportional to x and a is directed oppositely to x, right? So this is the important thing about simple harmonic motion. Now you have to remember that when we started the discussion, we started by saying that there is a particle performing a uniform circular motion with angular velocity omega, but now we are slowly moving on to the fact that we are more interested in discussing the x component of the position of the particle. So basically this angular velocity is omega. So that means what? When you consider the x component of the position of the particle, then angular velocity is called angular frequency. Okay, so the circular motion, for the circular motion omega is angular velocity, but we are interested in the x component of the circular motion, so for that it is called angular frequency. So omega is the angular frequency, t is the time period, okay, and what is capital A? Capital A is called amplitude, okay, capital A is called amplitude. So capital A is synonymous with the maximum displacement from what we call the mean position or the equilibrium position. Now that seems to be a bit of a surprise, like where did this come from, mean position, equilibrium position? We never said anything like that before. Well, the problem is that in order to analyze any oscillatory motion, you will have to use a lot of calculus. A lot of calculus will have to be used. So if you want to avoid using calculus and yet analyze oscillatory motion, then this is the alternative option. In this method, you can take a situation of circular motion and the x component will be the thing which we will analyze for oscillatory motion, right? If you don't do it this way, then you'll have to use a lot of calculus. So I am saying let's avoid that, because that calculus usage is not ultimately going to help you to solve any problem. So the point is that suppose if you consider one of the most famous examples of simple harmonic motion is none other than the pendulum. So in a pendulum, so if you now try to discuss whatever we have said here in the light of a pendulum, so how does it stand? So capital A is the extreme right. So the particle started the journey from extreme right, so capital A. Then it came to a place where x became 0, so it came to this place. So this place where x is 0, this is called the equilibrium or the rest position. Why? Because in a pendulum, if you do not cause any disturbance, then the pendulum will be exactly like this. So this is called the rest position or the equilibrium position. After that it goes to minus a, after minus a it comes back to 0, after 0 it again goes to a. So in a pendulum, the oscillation is from capital A to 0 to minus A back to 0 and then again to A. So that is why if you look at a pendulum, then you understand that why capital A is called amplitude, because from the rest position it is the maximum displacement on either side, on the positive side, on the negative side. So now after listening to this, now it's very clear why capital A is called amplitude, because pendulum is the actual simple harmonic motion, and analogous to that is this discussion of the x component of circular motion, right? So these are the terms. So time period, angular velocity, time period, angular frequency, amplitude, right? These are preliminarily that these are the terms. And acceleration is minus omega square x, right? Now basically what happens is that when we discuss the simple circular motion, we said that the journey begins from P, but the journey, it is not compulsory that the journey will begin from P. The journey can begin from a point above the point P also. So the journey can begin from some other point also. So the journey can begin from some other location whose angular displacement with respect to P is delta. Okay, so suppose this is P and this is P dash, and this is omega t, this is P double dash. So the journey started from P, then after the particle reached P dash, the particle started the journey from P dash, the angular displacement is delta, and then omega t later it came to P double dash, right? Now if that is the case, then this entire discussion which we did over here, it will become like this. X equal to A cos omega t plus delta then velocity is minus A omega sine omega t plus delta, then acceleration is minus omega square A cos omega t plus delta. So acceleration is again coming minus omega square x. Now the point is that this is the general form of this. This is a very specific one. This one is a specific one. This is if the the simple harmonic motion starts from the extreme position. So this is a very specific discussion, and this is the general discussion, right? This is the general discussion. So in the general discussion, suppose if you take delta as pi by 2, incidentally, we are liberally using calculus. We are doing dx dt dv by dt. You know, in calculus the angles are in radian. In calculus there is nothing called degree. So the delta value, suppose it is pi by 2. So if the delta value is pi by 2, that means the oscillation is starting from here. Right? If delta is pi by 2, the oscillation is starting from here. From this particular place the oscillation is starting. So if you put delta is pi by 2, it will become A cos omega t plus pi by 2. All of you know that cos any angle plus 90 is minus sine. What is cos 90 plus theta? Minus sine. So if you put delta equal to pi by 2, then x will be A cos pi by 2, right? If you put delta equal to pi by 2, then x will be equal to A cos pi by 2. So, A cos omega t plus pi by 2. Now, all of you know extremely well that cos 90 plus theta is how much? Minus sin theta. So, this will become minus A sin omega t. Now, literally what does minus A sin omega t mean? It means that the simple harmonic motion starts from the mean position and it goes to the left, like the pendulum. Suppose this is a pendulum, So it started the journey from x equal to 0 and then it started going to the left. So this minus a sine omega t, it simply means that it started the journey from x equal to 0, because if I say pi by 2, that means it's over here. Over here means it's just above the origin, so x is 0, right? And it is minus, so it's going to the left, correct? But from all the understanding of science and maths, like how many formulas do you know which begins with a minus? So a formula normally doesn't begin with a minus. So what we will do is we'll forget about the minus and we'll replace it with a plus. So in that case, x equal to a sine omega t, v is equal to a omega cos omega t, and acceleration is minus a omega square sine omega t. So x is a sine omega t, v is a omega cos omega t, acceleration is minus a omega square sine omega t. And what we will now do is we will now call these as formula number 1, 2 and 3, right? So why, I mean, we have discussed this, we have discussed that. Why are we calling these three as formula number 1, 2, 3? Why? See, whenever you say any type of motion, oscillation, whatever, there has to be a beginning. It has to begin from some time or somewhere. So before it began, everything was at rest, correct? So it makes sense to analyze simple harmonic motion from the position of rest. So we will say that it's convenient to discuss the simple harmonic motion from position of rest. So x is a sine omega t, v is a omega cos omega t, acceleration is minus a omega square sine omega t. So these are the values of x, v and a. So x is a sine omega t, v is a omega cos omega t, acceleration is minus a omega square sine omega t, okay, and time period is 2 pi by omega, okay, time period, this is also a formula, time period is 2 pi by omega, right? So I am calling time period formula as number 4, correct? Okay, now what happens is that if you want to keep it general, you have the option, you can keep it general. So you can just add one plus delta here, just like you did omega t plus delta here, you can just add one plus delta here. You have that option, you can do it. So delta is called the initial phase, and it is also called the epoch. Okay, delta is called the initial phase, it is also called the epoch. See, what I am trying to say to all of you is that we should keep a set of formulas which are maximum user friendly. Too much clutter of information is not going to help. There's nothing very difficult about this, but the thing is that when you are ready with the chapter, what is a formula which should be there in your brain readily? So I think these 1, 2, 3, these are the best. Okay. Time period is 2 pi by omega. Delta is called the initial phase or epoch. Okay, if you need to have a general discussion, you can say delta. Right. Okay, then what else is there? So we have got all these values. Now what else is there? See, the x is given in terms of time, velocity is given in terms of time, but sometimes it is preferable for us if velocity and x are related to each other and not to time. Sometimes it is preferable. So what we can do is that this equation, the first and second equation, sin squared omega t plus cos squared omega t is 1. So x squared by a squared plus v squared by a squared omega squared is 1. So V is omega root a square minus x square. So cos sin square omega t plus cos square omega t is 1. Sin square omega t is x square by a square. Cos square omega t is v square by a square omega square. So the total of them is 1. So V is omega into root over a square minus x square. So this is the formula number 6, the formula to find the instantaneous velocity in terms of displacement, right? Okay, now in any simple harmonic motion, we have defined it that it is a oscillatory periodic motion in which acceleration is proportional to displacement and directed oppositely to it. But what is the force which is causing the simple harmonic motion, right? So for example, if there is a pendulum, okay, you give the pendulum bob a slight push and then it will go on oscillating. So you gave it a push, it went some distance, but then it started coming back. So there is a force which is causing the oscillatory motion. I told you oscillatory means to and fro. So you gave it a push, it went some way, but then it started coming back. So if it is coming back, there must be something which is bringing it back. So that something is called the restoring force. And how do we find the restoring force? So acceleration equal to minus omega square x. So you multiply both sides with m. So ma is minus m omega square x. So ma is force. And m omega square, we will replace it by a constant k. Okay. So acceleration is minus omega square x. So ma is minus m omega square x. So ma is force. Force is equal to minus k into x. So ma is the force which is responsible for the simple harmonic motion, and m omega square is called the force constant. Okay. So m omega square is called the force constant. So k is called the force constant of the simple harmonic motion, and so we can now see that k is m omega square and omega will be equal to root over k by m. So k is called the force constant and k is m omega square, so omega is root over k by m. So this omega is root over k by m is a relation between omega, k and the mass of the particle which is executing simple harmonic motion. So that means we can now also say that simple harmonic motion is oscillatory periodic motion in which the force is proportional to displacement and force is oppositely directed to displacement, because F is proportional to x and there is a minus sign, so it is directed oppositely to the displacement. So that is also another way of describing simple harmonic motion. This force is also called restoring force, because if you make the simple harmonic motion happen, then this force will be created by itself, rather by the body as a reaction to the cause. The effect is this restoring force. It will try to restore the body to its equilibrium position. That is why it will keep oscillating. Now this force constant is sounding a lot like spring constant. It's sounding a lot like, so it is sounding a lot like spring constant, right? So what is happening is that the spring constant is basically something which is associated with any spring. So for example, that if there is a spring, suppose there is a spring, so you exert a force, so the spring will undergo, you exert a force on the spring will undergo an elongation. Okay, the spring will undergo an elongation or compression, either elongation or compression, right? So you have exerted a force F and it will elongate by suppose X. So when you elongate a spring, then a restoring force is built up inside the spring which tries to bring the spring back to its original state. So spring oscillation is also an example of simple harmonic motion. So if you extend or compress a spring and leave it, it will oscillate, and that equation is exactly identical to the force equation of simple harmonic motion. So here we call it spring constant, Here we call it force constant. Now speaking of spring, so there are two situations of combination of springs. So here there are two springs of spring constant K1, K2. They are called series. They are called springs in series. So here in this diagram, K1 and K2 are the spring constant. The springs are in series. So when the springs are in series and you are exerting a force, so they are in series. So the force will be common to both of them. So suppose the force is F. So force you can say minus K1 x1. You can say minus K2 x2. The force will be same for both the springs. So for this spring it will be minus K1 x1, for this spring it will be minus K2 x2. And therefore you can say that the overall displacement is x1 plus x2 so minus F by K1 and minus F by K2. So F will be minus K1 x1 minus K2 x2. So x1 plus x2 will be minus F by K1 and then minus F by K2. So what you can do is x you can write as minus F by K. So minus F by K is minus F by K1 minus F by K2. So finally K is coming to K1 K2 by K1 plus K2. So whenever you have springs in series, the equivalent spring constant is K1 K2 by K1 plus K2. Whenever you have springs in series, this is the equivalent spring constant, right? Now suppose you have springs in parallel. Suppose you have springs in parallel. So if you have springs in parallel, then both of them will have the same displacement. So F will be minus K1x. F1 is minus K1x, F2 is minus K2x. So they both will have the same displacement. So F you can say is F1 plus F2. So minus Kx is minus K1x minus K2x. So ultimately we will get K is equal to K1 plus K2. So this is the two formulas, okay? These are the two formulas for spring combination, right? So I can call both of them collectively as formula number 8, right? So this is the formula for parallel and this is the formula for series. So whenever two springs are, this is the formula for series and this is the formula for parallel, Okay, this is series, this one is series, and this one is parallel. So whenever you have combination of springs, then if they are in series, the equivalent spring constant you will have to do exactly like you used to do parallel in current electricity. So if there are two springs, it will be K1 K2 by K1 plus K2, and whenever the two springs are in actually in parallel, that time the equivalent spring constant will be the same as you used to do series in electricity, so K1 plus K2. So this becomes our formula number 8. Okay, now I want to clarify something. This diagram is very suggestive. The way I have drawn, just one glance and you know it is series. And this diagram also, if you see the diagram at one glance, you know it is parallel. So this diagram straight away series, this diagram straight away parallel. So at a glance you know this is series, that is parallel. Now there is another diagram for parallel which is not immediately clear that it is parallel, but that is also parallel. That is if the springs are like this. So suppose if the springs are like this, then what will happen? This is the mass in the middle. So this is K1, this is K2, this is the mass in the middle. So if you push this by x, this will get elongated by x. So how much you push this, that will get elongated by that much. So this is also an example of parallel. So parallel can be like this, parallel can be like this also. Both of them are diagrams for parallel, right? So this one and this one both are applicable for parallel. Okay. Okay, obviously when we are having a discussion of any chapter of physics, one primary concern is energy, always, no matter which physics chapter you are doing. Energy is always a primary concern. So, kinetic energy of simple harmonic motion. So, kinetic energy of simple harmonic motion, the formula is half mv square, and in this formula v is this. So, v square will be equal to this. Okay, so half mv square, so half m, and v square is omega square into a square minus x square, right? So this is the formula, and this is the kinetic energy of simple harmonic motion. Now you understand that mechanical energy is a sum of kinetic and potential energy. So if there is kinetic energy, there must be some formula for potential energy, and therefore the two of them will give me the mechanical energy. So now we need to sort that out. So number 8, this is series and this is parallel. Okay, so kinetic energy of simple harmonic motion is this. So this is kinetic energy of simple harmonic motion. Okay, how do we find potential energy? How do we find total energy? See, there are two ways of looking at it. You can do one thing. You can say that potential energy we can use find it by using the concept of conservative force. So you know that this restoring force is a conservative force, right? And when we were doing spring, the spring potential energy, the answer had come half k x square. So the potential energy you can say is half kx square. So I hope this is clear to everyone. Once again I am reminding you what I am talking about. You see, this is a restoring force. Restoring force is a conservative force, right? So that means you can apply conservative force into dx and then integrate it, just like we used to do potential energy in work energy chapter, and also the same way that we derive potential energy of a spring, and that formula was half kx square. So in this formula, k is m omega square. So ultimately potential energy is half m omega square x square. So the kinetic energy is half m omega square a square minus x square. Potential energy is half m omega square x square. So the total energy, it will be equal to kinetic plus potential. So the total energy, this is kinetic, this is potential. So the total energy will be kinetic plus potential. So that will be half m omega square a square. So kinetic energy is this, potential energy is this, and total energy of simple harmonic motion is this. So this becomes formula number 9, right? So this is formula number 9. Okay. Now in simple harmonic motion, I have already told you that one of the best examples and most well-known examples of simple harmonic motion is obviously none other than the pendulum. So in a pendulum, what happens is that so this is the acceleration due to gravity g. This angle is theta, this is theta. So this is g cos theta, this is g sin theta. So the restoring force, the force which will bring the bob back, is minus mass into g sin theta, because you can see that g cos theta will be along the string, so it will not restore. G sin theta will restore. So the restoring force F will be minus mg sin theta. Suppose the length of the string is L, and suppose the displacement from the equilibrium position is x. So sin theta, for very small displacement we can write it as theta. Now one thing you all have to remember, this is very important, that by default in entire simple harmonic motion the displacements are assumed to be very small. If the displacements are not small, then you cannot have any simple harmonic motion. It will be very arbitrary type of motion. Okay, there will not be any particular methodology or formula or any method, any calculus method, nothing will work. So the displacement has to be very small. So sin theta is approximately equal to theta, and you know that for radian measure, theta is arc length by L. So arc length you can take it as x by L. So force is minus mg into x by L. But you are also aware that for simple harmonic motion the force is minus kx. So minus kx is minus mg into x by L. So ultimately what will happen? That k is m omega square. So m omega square is m into g by L. So omega is root over g by L. So time period is 2 pi root L by g. Okay. So minus kx is minus mg into x by L. So k is m omega square. So m omega square is mg by L. So omega is root over g by L. So time period is 2 pi root L by g. So this is the famous formula of simple harmonic motion. That means the time period is 2 pi root L by g, right? So this is the derivation of that. Now the derivation of time period of a pendulum which we did just now, this derivation, it can be done in another way. In fact, you can have another discussion on simple harmonic motion by considering angular parameters. So just to give you an idea, so linear motion is x equal to a sin omega t, angular motion is theta equal to theta 0 sin omega t, linear motion is v equal to a omega cos omega t, angular is omega equal to theta 0 omega into cos omega t. Then linear will be this, acceleration will be minus a omega square sin omega t. And angular acceleration will be alpha equal to minus theta 0 omega square into sin omega t. So acceleration is minus a omega square sin omega t, and here angular acceleration is minus theta 0 omega square sin omega t. So kinetic energy is half m omega square a square minus x square. Potential energy is half m omega square is x square. Total energy is half m omega square a square. So these are the values of kinetic, potential and total energy. And the 10th formula is okay. So coming back to linear and angular. So these are the things. Then you come to number 4. F is equal to so in linear motion F is minus kx, and in angular motion torque is minus k theta. So these are the and then of course the time period. Now before I tell you time period, in linear simple harmonic motion omega is root over k by m, So time period 2 pi by omega is 2 pi root m by k. So the next one is time period. So 2 pi root m by k. And here time period is 2 pi root I by k. So here time period is 2 pi root m by k, here time period is 2 pi root I by k. So these are the formulas of linear simple harmonic motion, and corresponding to this, these are the formulas of angular simple harmonic motion. Now the pendulum which we discussed, you can solve pendulum by this angular method also, right? You can do that. So let us see how that is done. So torque is mg into OP sin theta. So OP is L. So torque is mg into L sin theta. And by the way, this is a restoring torque. So minus mgl sin theta. So minus mgl into theta. And meanwhile, you know that torque is equal to I alpha, and I, it will be ml square. So ml square alpha is minus mgl theta. So alpha is coming minus g by l into theta. But you know that alpha is minus omega square theta. So omega is root over g by l. So time period is 2 pi root L by G. So this is another alternative method to derive time period. So once again I am saying the simple harmonic motion is happening. So this is the weight of the bob mg, this is the angular displacement theta. So the restoring torque will be mg into this distance, so that is OP sin theta. So OP is the length of the pendulum L, so minus mgl sin theta. So sin theta and theta both are same, so minus mgl theta. So torque is I alpha, that is minus mgl theta. Meanwhile, moment of inertia is ml square, so ml square alpha is minus mgl theta. So alpha is minus g by l theta, but alpha is minus omega square theta. So omega is root over g by l, so time period is 2 pi root l by g. So this is another formula, another way to derive time period of a pendulum using angular simple harmonic motion. So if you use angular simple harmonic motion, then also it is coming 2 pi root L by G, right? Now, is there any other use of angular simple harmonic motion, or is it that just like this it is an alternative method to study the oscillation of a simple pendulum, or is there any other use of angular simple harmonic motion? So the answer to that question is that angular simple harmonic motion can be used to analyze a physical pendulum. So what is a physical pendulum? Physical pendulum means what? Its action will be like a pendulum, but it's not actually a pendulum. The action will be like a pendulum, but it's actually some other type of a body, not a pendulum, some other body. So let us say Okay, so there is a some type of a body, some shape like this. So it is suspended about a point. Okay, it is suspended about a point. Like suppose there is a very weird shaped body and there is a nail on the board or something. So it is suspended from there, and then you slightly, make it oscillate. So this is the angular displacement, this is the weight mg, and this is the axis. Okay. So, so now we have to consider the torque about the axis of rotation. So this is the axis. We have to consider the torque about the axis. So torque will be mg into OD So mg into OC sine theta so mg into L sine theta. So this will be the torque. So torque is minus mg L sine theta. So alpha is minus mg L sine theta by I. So minus omega square theta. So torque is 2 pi root I by mgl. So alpha is minus mgl sine theta by I. So minus omega square into theta. So time period is 2 pi into root over of I by mgl. So this formula 2 pi root I by mgl, this formula we got, this is for a physical pendulum. Now in this formula if you put I equal to ml square, suppose in this formula if you put I equal to ml square, then it will become normal pendulum. Like just remove I and put ml square, you will get normal pendulum. So this is a physical pendulum. So physical pendulum is now therefore going to become our next formula. So time period is 2 pi root I by mgl. Okay. So physical pendulum, the time period is 2 pi root I by mgl. So this is the time period 2 pi root I by mgl, and therefore T will be 2 pi into root over I by. This is for physical pendulum, right? And physical pendulum you can say is a more versatile formula, because in this if you just put I equal to ml square, you will get the answer of simple pendulum. So these are the formulas, right? Physical pendulum is this. Okay, now we come to the next topic, combination of simple harmonic motions. Isn't it possible that a particular body is simultaneously undergoing two simple harmonic motions? It is possible, right? There is a body, and simultaneously that body is undergoing two simple harmonic motions. That is very much possible. So, in this combination of simple harmonic motions, um, so in combination of simple harmonic motions, suppose there is a body, simultaneously it is undergoing two simple harmonic motion. X1 is A1 sin omega t, X2 is A2 sin omega t plus delta. Simultaneously it is having both the simple harmonic motions, right? So in this, if you combine the two, so x1 plus x2 will be a1 sin omega t plus a2 sin omega t plus delta. So a1 sin omega t plus a2 sin omega t cos delta plus cos omega t sin delta. So sin omega t into a1 plus a2 cos delta plus cos omega t into a2 sin delta. So suppose this one you call it as cos theta and this one you call it as sin theta. So sorry, this one you call it as a cos theta, this one you call it as a sin theta. So this will become a sin omega t plus theta. Okay, I am repeating again. The particle is having two simultaneous simple harmonic motions. So a1 sin omega t and a2 sin omega t plus delta. So I have expanded it. Then I took sin omega t common. I took cos omega t like this. So this whole thing is a cos theta. This whole thing is a sin theta. So a sin omega t plus theta. So this is x1 plus x2. Now with this value of a sin omega t plus theta, I will have to find what is a and I will have to find what is theta. So a cos theta is this, a sin theta is this. So from there I can say that tan theta a2 sin delta by a1 plus a2 cos delta. So a sin theta is this, a cos theta is this. So tan theta is a2 sin delta by a1 plus a2 cos delta. So this is tan theta. Okay, that is number one. And number two, the value of a. So if this is a cos theta, this is a sin theta, then a will be root over of square of this plus square of this. So the value of a will be root over of a1 plus a2 whole square, a1 plus a2 cos delta whole square plus a2 sin delta whole square. So the value of a is coming root over a1 square plus a2 square plus 2a1 a2 cos delta. So the value of tan theta is this, the value of a is this, and this actually looks very similar to the superposition of two waves. So you could say that superposition of two simple harmonic motions follows the same logic as superposition of two waves. So the two simple harmonic motions, their combination gives a new simple harmonic motion A sin omega t plus theta, where tan theta is this and A is equal to this, right? So this is the thing. Okay, now we come to the next part of the chapter, that is damped oscillation and forced vibration. So suppose the equation of simple harmonic motion F equal to minus BV. So m dV by dt is minus, one thing, in damped simple harmonic motion, exactly what happens? In damped simple harmonic motion, you see throughout the discussion today, we have sort of assumed that there is nothing to slow down the simple harmonic motion. The simple harmonic motion is happening in vacuum. There is nothing to slow it down, we have assumed. Now in case of damped simple harmonic motion, what happens? That there will be some force which will slow down the simple harmonic motion, that is called damping force. Typically viscosity, air resistance, these are responsible for damping. So it was found that the damping force is proportional to the velocity and oppositely directed to it. So F will be minus BV. So m dV by dt is minus kx minus BV, right? So once again, this is the damping force. Okay, this is the damping force F equal to minus BV. And due to this damping force, the resultant equation will be m dV by dt is minus BV minus kx. So x will be equal to A0 e to the power minus bt by 2m sin omega dash t plus delta So omega dash, the value will be this. So omega dash is approximately root over k by m is omega 0. That is if there is a small damping. Okay, so let's just discuss this again. So as I told you that throughout the chapter today, we have assumed sort of that the simple harmonic motion is not going to be hindered by any resistance or any dissipation of energy, nothing, viscosity, nothing is there. But practically that is not possible. So the damping force is given by F equal to minus BV. So m dV by dt is minus BV minus kx. So x will be a0 e to the power minus bt by 2m sine omega dash t plus delta. This is the equation. Now the problem is that these equations require very advanced calculus which is beyond our scope of discussion. So the damping force is proportional to velocity and oppositely directed, so F is minus BV. Due to the damping force, the resultant force equation of the particle is m dV by dt is minus BV minus kx. The solution of this involves a lot of advanced calculus. Answer is a0 e to the power minus bt by 2m sine omega dash t plus delta. Omega dash is again given by a very big formula, root over k by m minus b by 2m whole square, where k by m we all know is the natural angular frequency. So k by m we can write omega 0 square. Now if the damping is very small, and there is damping but it is very small, we can neglect b. So then omega dash and root over k by m will be almost the same. That means omega dash and omega 0 will be almost the same. But even then the amplitude will decrease. So to give you an idea, in a simple harmonic motion, the amplitude is not supposed to decrease, it is supposed to be like this. But if you follow this formula, then the amplitude will decrease. Okay, so if you follow this, the amplitude is the same, but if you follow this, the amplitude is decreasing. Okay, so in a simple harmonic motion, if the amplitude decreases, if b is very small, then omega dash is approximately equal to omega 0, and the amplitude is a0 e to the power minus bt by 2m. Right? So this is for damped oscillation. Okay, next we come to forced vibration. So, if there is a situation where you want the oscillation to sustain, there is damping, but due to damping you don't want the oscillation to die out, you want the oscillation to sustain. So you will have to apply an external periodic force that is called driving force. So F0 sine omega t is the driving force. So m dV by dt is minus kx minus bv plus F0 sine omega t. So the solution of this equation is x equal to a sine omega t plus 5. Okay, so what we say, the theory behind these type of oscillations is that the natural oscillation will die out after some time, and after it dies out the formula will be x equal to a sine omega t plus 5. So this is called forced oscillation. Okay, this is called forced oscillation. So amplitude is f0 by m root over omega square minus omega 0 square whole square plus b into omega by m whole square. So what happens is that in case of forced oscillation, the energy that is lost due to the damping is compensated by the work done by the damping force. So this is the formula. Now so this amplitude becomes maximum when omega is root over omega 0 square minus b by 2m whole square, and this condition is called resonance. So what is the definition of resonance? It is the condition for maximum amplitude. So once again, when you have a damped simple harmonic motion, you want to sustain it. So you apply a driving force. Due to the driving force, this is the equation. After the natural oscillation dies out, this is the equation. It is called forced oscillation. This is the amplitude, and maximum amplitude happens when omega is this. That is called resonance. So for small damping, omega 0, omega dash approximately equal to omega 0 equal to approximately equal to omega. So the applied frequency approximately equal to natural frequency, right? So that is the condition of resonance. So when there is a small damping, then omega 0 and omega are almost equal. That means applied frequency is almost equal to natural frequency. When that happens, amplitude is maximum. That condition is called resonance. So this is the condition for resonance. Okay. So we have completed the theory portion of this chapter fully. The last part especially has been coming quite often in recent competitive exams. The damped oscillation and the forced vibration, that has been coming quite a lot in the competitive exams recently. So anyway, we have managed to complete the topic fully, and that would now bring us to an end of this session. So I'll conclude the session now. Okay, I'll end the meeting. Thank you. Bye all of you.